welcome back to another explainer. Every single year, pharmaceutical companies lose absolute millions to batch failures. So today, we're stepping into the lab, putting on our detective hats, and conducting a full-blown scientific autopsy of formulation failures. If you've ever stood there wondering why a perfectly calculated formulation suddenly crumbles, cracks, or completely loses its color right on the production line, well, you are in the exact right place. We're going to look really closely at the anatomy of tablet defects, going layer by layer to uncover exactly what goes wrong when the pressure is literally on.
Okay, let's dive into this. Here's our roadmap for today. We'll start with the anatomy of defects, move through tableting process issues, then hit excipient and material defects. After that, we'll look at machinery and mechanical failures, dive deep into tablet coating defects, and finally wrap it all up with our final diagnosis.
Section 1. The anatomy of defects, visualizing the blueprint.
All right, before we can actually fix a problem, we really need to understand the blueprint. Take a look at the overlap in this diagram. For uncoated tablets, we're dealing with things like capping, lamination, and mottling. For coated tablets, we see defects like blistering, crattering, and blushing. But right in the middle, that's our overlap: chipping, cracking, and picking. Now, it's absolutely critical to understand that the vast majority of these visual defects come down to pretty straightforward things: inadequate fines, improper moisture in your granules, or just a faulty machine setting. But functional defects, man, those are born from faulty formulation. Solving them requires an incredibly in-depth, almost forensic knowledge of both your granulation processing and the physical tablet presses themselves.
Section 2. Tableting process defects, the battle of compression.
Inside the tablet press, it is an absolute battle of physical forces. You can see the distinct structural failures happening here. Take capping, for example, where you can clearly see the partial or sometimes total separation of the top or bottom crown of the tablet right off the main body. And then there's lamination, where the tablet actually separates into two or more distinct horizontal layers. It almost looks like a piece of flaky pastry. Both of these represent a catastrophic failure of cohesion, but they leave completely different mechanical fingerprints.
So how exactly do we diagnose and treat these? Well, capping is often caused by entrapped air in the granules or just really rapid decompression. Lamination, on the other hand, frequently points to inadequate binding within the granules themselves, or maybe your compression speeds are just way too high, or you've over-lubricated the mix. To remedy these fractures, we literally have to relieve the pressure. We buy some time by increasing the dwell time so those particles can actually bond. We dial back the pre-compression force and turret speed, and we fine-tune that binder concentration while, of course, being super careful to avoid excessive lubrication.
Okay, let's look at another mechanical nightmare. Notice those compromised pitted surfaces? We call this picking and sticking. Picking refers specifically to material actually sticking to the punch faces, physically tearing away a little piece of the tablet surface. Sticking is when those granules adhere straight to the die wall itself.
The autopsy on picking and sticking usually reveals a failure to balance moisture and friction. The primary culprits here: low moisture content in your granules, inadequate lubrication, or honestly, sometimes just rough, worn-out punch surfaces. The fix is this incredibly delicate balancing act. You've got to adjust the moisture to optimal levels so your granules aren't overly dry, dial up your lubricant concentration, and make sure your machinery is actually up to par by using smoother punches or just adding anti-adherent agents right into the mix.
Section 3. Excipient and material defects, chemical incompatibilities.
Sometimes the hardware is perfectly fine, but the chemistry is basically at war with itself. This right here is mottling. The surface is scarred by this completely uneven distribution of color. It looks patchy, it looks totally unprofessional, and that immediately reduces its acceptability for the end user. No one wants to take a pill that looks like a bad tie-dye experiment.
Eradicating mottling is all about chemical troubleshooting. First step, you've got to identify any dye incompatibilities between your colorant and your excipients. A lot of the time, the absolute easiest remedy is simply switching to a lake pigment instead of using a water-soluble dye. It's also super vital to improve your mixing process to ensure that dye is distributed completely evenly. And crucially, you have to match the particle sizes of the active drug and the excipients. If they are vastly different sizes, they're going to segregate, and they will pull that color right along with them.
Section 4. Machinery and mechanical defects, when the press fails.
So what happens when the physical hardware vibrates or gets misaligned?
Put your detective hat back on for a second and look closely at the ghosting on these logos. See that double stamping? We literally call this defect a double impression. It happens when the tablet surface takes a second, completely unintended strike from the punch. This double impression is usually caused by the free rotation of the lower punch during the ejection phase, or sometimes just from excessive machine vibration. The fix here is strictly mechanical. You've got to stabilize the equipment, use keyed punches to stop that free rotation, and deploy anti-rotation devices. And while we're talking about the press, machinery flaws can also lead to massive weight and hardness variations. If your granules have poor flow into the die cavity or an uneven size distribution, your tablets are going to be wildly inconsistent. You remedy this by strictly calibrating your machine, making absolutely sure you have uniform granule size, and using feeders to force a consistent flow.
Here's another machinery-induced trauma: cracking. If you mentally zoom in on the surface, you can see these fine micro fissures just spreading right across the center.
Cracks are essentially stress fractures. They form because of rapid decompression as the tablet is forcefully ejected from the press, or because the initial compression force was just way too high for the material to handle. It also heavily points to inadequate plasticity of the granules. Healing these fissures takes a two-pronged approach. Mechanically, you've got to adjust your decompression settings and reduce that raw compression force. Chemically, you need to go back and revisit your formulation to give your granules a bit more plasticity so they can actually flex a little rather than just snapping under all that pressure.
Section 5. Tablet Coating Defects. The final layer.
All right, we've left the heavy compression machinery behind, and now we're entering the highly sensitive, rapid-fire world of film coating. First, we have blistering, which looks exactly like what it sounds like, a local detachment of the coating that forms these raised blisters. Contrast that with cratering, where you actually see a volcanic-like depression that exposes the raw core of the tablet underneath.
Even though they might look somewhat similar at a quick glance, their causes are totally distinct. Blistering is a heat issue. Gases get entrapped in or underneath the film because of overheating during spraying or right at the end of the coating run. This causes the film to lose its elasticity and just pull away. Cratering, on the other hand, is a moisture issue. It happens when the coating solution literally penetrates the tablet surface, especially at the more porous crown. That excess moisture causes a localized disintegration of the core. To fix blistering, you've got to use mild drying conditions. To fix cratering, you have to optimize drying to prevent that moisture disruption and increase the viscosity of your coating solution so it doesn't soak in so quickly.
Now here we have two more really distinct aesthetic failures. Notice those distinct white specks scattered all across the colored film? That is called blushing. Contrast that with blooming or hazing, which gives the polished tablet this incredibly dull, fogged appearance all over. It kind of looks like a steamed-up bathroom mirror. The chemical diagnosis for blushing is pretty clear. Those white specks are actually particles of polymer that have precipitated, usually as a result of an excessively high coating temperature. To cure blushing, you just have to drop that drying temperature. Plus, you need to avoid using sorbitol with certain polymers, like cellulose ethers, which can actually trigger this precipitation. As for blooming and hazing, that fogged appearance is also driven by high temperatures during formulation or just exposure to high humidity. So strictly controlling your environmental humidity is the absolute key remedy there. Finally, we have twinning. This is when two or more tablets literally stick together. This usually happens when your drying process is inefficient, or maybe you're applying the coating solution at a much higher rate than the pan can actually evaporate it. You are basically gluing the tablets together. Obviously, that's not great for the patient and definitely not great for their batch yield. The remedy here is adjusting the pan speed, tightly controlling the drying rates, and choosing appropriate tablet shapes right from the start that don't easily present flat surfaces to one another.
Section 6. Summary and final diagnosis.
Let's bring this cinematic autopsy to a close. So the crucial point I really want you to take away is this. Every single defect we've examined today, from a cracked core to a blistered film, has a highly distinct mechanical or chemical fingerprint. Visual